Following up on Elon Musk's post yesterday, Tesla insiders Ashok Elluswamy and Julian Ibarez just dropped the most revealing hints yet about how fast Tesla's new AI4 hardware actually is, including a crazy 1 millisecond per million pixels claim. When you combine that with new camera resolution details and what Grok's analysis might imply, the picture that emerges is that Tesla is now operating near the absolute physical limits of real-time robotics. And the really wild part, the same capability extends directly to Optimus. Let's take a look. Before we start, a quick shout out to my channel sponsor Joa. They make the best accessories for your Tesla and other EVs, and they have amazing warranties and customer service too. I use their accessories daily. Be sure to check the link in the description to get 5% off a fan-cooled phone charger, a portable tire inflator, a fold-out laptop table, and so much more. Oh, and they make perfect gifts for your EV-loving friends too. So check out my link, get 5% off, and now let's get back to it. Hey y'all, it's Dr. Know-It-All. So we're going to start with Elon's post from November 23rd yesterday. I'm not going to go back over it again because you can catch that video right up here. This is basically part 2 of that video. I will leave a link in the description as well so you can easily click that one and then come back to this one because I think it's probably a good idea to have that information as background before we go to today's video. But basically Elon lays out the roadmap and then Ashok and then Julian actually add on to that. So that's what I want to talk about today and then extend that with some speculation from Grok and ChatGPT and see if we can figure out about how fast these systems are operating, what the bottlenecks currently are, and how this all translates to Optimus, the humanoid robot, which has a different input and output space. So yesterday afternoon, of course, just after I released my other video, Ashok responded to Elon and said, not to mention these chips are heavily co-designed with the Tesla AI software teams to achieve incredible performance while also beating by a large margin on performance per watt and performance per dollar. So I touched on this in my video yesterday. It's very, very important that Tesla has a hardware-software vertical stack. It's a little bit like NVIDIA with their CUDA software. They have a proprietary hardware-software stack, and the interaction between those two is critically important to why NVIDIA is doing so well in the general AI space right now. Now, Tesla can vertically integrate and refine things much, much more than NVIDIA because, of course, NVIDIA is a general-purpose GPU, while Tesla is able to make a very, very specific system on chip that can do exactly what they want and nothing else. For example, we recently learned from Elon Musk that Tesla actually does integer math rather than floating point math when they're doing on-chip inference, which saves a huge amount of memory and compute time. Anyway, Ashok continues, for instance, AI4, the thing that is currently in our vehicles, can process and understand 1 million pixels of streaming video within approximately 1 millisecond. That is a tiny amount of time. There's 1,000 of those per second, right? This is only achievable because the software and the hardware are designed together to achieve this performance point. And of course, Ashok is Tesla's AI lead. And this is followed up by another response, this one from Julian Ibarez, who you can see here is Tesla bot Optimus AI lead. So we are going to talk about Optimus today as well. He follows up with the latency of our autopilot computer, which is used by both Optimus and full self-driving. And of course, in the vehicles, we have 2 AI4 boards for redundancy, right? Because if one fails, you need something going 75 miles an hour to have a failover. While as far as the latest evidence indicates, Optimus only has 1 of these boards because if there is a failure, it's not nearly as critical as in a car, right? So you can get away with 1. But anyway, there's dual redundancy in the full self-driving in a car, while apparently the board is half the size and you only get 1 AI4 chip on Optimus. Not a big deal, but anyway, I just wanted to point that out. Anyway, the latency from photon hitting the sensor, in other words, light actually hitting the camera sensor, to it being processed by the neural network chip is extremely low. So that is all of the onboarding stuff. We're not talking about the complete process of decision making here. We're just talking about photons in to being able to process the image enough for the neural network that makes the decision to figure out what to do with that information. As Julian says, everything is optimized, everything is hardware accelerated as much as possible, no software stack overhead, which is really interesting, minimal image processing overhead. This is why the full self-driving stack is so reactive. This matters a lot for Optimus when we close the loop with vision. So hardware accelerated means it's sort of built into the hardware. It's baked into the chip itself so that there's not a software stack on top of it that has to be interpreted by the hardware. It's basically running on bare metal. And that, of course, is why he says there's no software stack overhead as well. And there is famously, and we've known this for a couple of years, minimal image processing overhead. This is something very unique to Tesla. There's no on-camera image processing. In your iPhone, if you take a picture, there is a ton of processing that happens before you see that image to make it look good to the human eye. But that adds a ton of latency and actually gets rid of a lot of the details that Tesla can actually use to basically, quote, see in the dark. When a processed image wouldn't even be able to make out details. The unprocessed image can see much, much better in very low light and very difficult to see situations. So there's the latency advantage of not processing the image, but the effective f-stops of the raw input image versus the processed input is also a lot higher. So there are multiple advantages to not pre-processing the data on camera before it goes to the first layer of neural networks. So now we're going to get into some speculation, and this is supported by both Grok and ChatGPT, and of course my research as well. But I wanted to let you know that I've combined these sources to try to give you the best information, but this is all speculative from this point out because we don't know all of the facts. So first, let's break down Ashok's claim. AI4, which is the current hardware we have, can process and understand 1 million pixels in approximately 1 millisecond. Now that sounds amazing until you realize how high a resolution these cameras are and the fact that there are 7 of them outside and 1 inside of your car. So it's a lot more than 1 million pixels per frame. Also, we should keep in mind that this almost certainly refers to the vision encoder only, not the decision-making process. So this is the front end, as I've discussed in the previous video. This is the part that takes the raw photons in and does some minimal neural network pre-processing. I said there's no pre-processing on camera, but you've got to do some pre-processing in a neural network encoder before you can send it on to the decision-making layer, because the decision-making layer has to know what it's looking at. And of course, the heavily co-designed with software aspect means that you have custom data paths in your network, you have fused operations, and there's no general purpose software overhead. In other words, you're not running Mac OS or Linux or something and then running this through that. There would be a huge amount of overhead to do that. You're just basically running this on bare metal, as close to that as possible. And then Julian's follow-up post talks about the extremely low photon to neural network latency. In other words, the ingest portion of it. That means there's no classical image processing pipeline. There's none of that stuff that's happening prior to the neural network grabbing the raw information out of these cameras. So that means you get direct raw to tensor operations, which, as I noted previously, allows the cameras to effectively see in the dark as well. And based on industry standards, this saves about 5 to 15 milliseconds of normal camera lag. So it would take a camera normally ingesting this information and pre-processing on camera 5 to 15 milliseconds to do that procedure. And of course, Julian states that this enables both rapid driving decisions and closed-loop humanoid manipulation for Optimus. So that means that Tesla has effectively solved the camera to neural network bottleneck that other AV companies are still struggling with at present. And the raw pixel throughput isn't just compressed, it's actually scheduled to match control requirements, which is very important. You need a level of determinism in terms of when things are going to arrive at the neural network in order not to get spurious output signals. You want to have things arrive on time, and that's very, very important. So now we turn to even more rampant speculation, which is actual camera resolution for AI4 currently. The word on the street has always been that these cameras are all 5.4 megapixels, but that might not actually be the case. And even if the raw image resolution is 5.4 megapixels, actually some of the cameras might only be about a quarter of the resolution. Now, as far as we know, the bulk of these cameras, around 80%, are being built by Samsung, with LG supplying about 20%. And it's possible other third-party companies are supplying either a few other cameras or parts of the cameras that are being utilized by Tesla. So that's where they're coming from. So the best resolution estimates that we have are that the front-facing cameras, the trio that's right above the rear view mirror, that's the front narrow camera, the front main camera, and the front wide camera, are all running about 5.4 megapixels or 2896 by 1876 pixels. So those are very, very high resolution. That's very important because those have to see in the distance, right? They have to see away from where the vehicle is, potentially up to like a half a mile or so. They need to be able to see very, very far away, to see lights, to see pedestrians, to see crossing traffic, all of that stuff. So that, of course, is critical that they have very, very high resolution. But the interesting information is that there is word on the street that the side repeater cameras are only 1.2 to 2.3 megapixels because they mainly provide lateral situational awareness and don't need to have nearly the resolution. And the B-pillar cameras, which are responsible for seeing, sideways when you're up at an intersection or something, run at about 2 to 2.3 megapixels. And additionally, the rear camera also runs at approximately that resolution as well. And for the rear camera, that's being used when you're backing up and stuff, so you're going relatively slowly. You're close to the objects like a curb or something, and so you don't need to be able to see really, really far away. Those cameras can operate at a lower resolution, and apparently they do. It's unclear whether they're manufactured that way or whether Tesla is just sort of cropping down the image internal to the camera prior to sending it off to the neural network. And again, this is all speculation. And then, of course, you've got the cabin camera, the interior camera that looks at your face. That's not part of the FSD path, but the word on the street is that runs at about 1 megapixel, which is perfectly fine for seeing inside of the cabin. So altogether, if this is correct, that gives you somewhere around 35 to 40 megapixels or million pixels coming in per frame. And that means if a shock statement of 1 million pixels per millisecond and you don't do any kind of compression or anything, that's 35 to 40 milliseconds of delay just to ingest all of that image data. So clearly Tesla is compressing that image data down prior to it going to the neural network, because otherwise we would have blown our entire 30 millisecond budget, which is about what they have to run at to keep at between 30 and 36 frames per second. We would have blown the whole budget just by doing the ingest portion. And speaking of that, there is some evidence that the hardware 4 cameras are operating on the 30 to 36 hertz range depending on the camera type, whereas the older hardware 3 cameras were all fixed rate at 36 hertz. So Tesla might have given themselves a little bit more range by reducing the frequency down to 30 hertz, which allows them a little bit more time to do all of this processing and make a decision. So how does Tesla compress this 38 megapixels down to a size where it can actually ingest this information in just a few milliseconds? Well, first of all, and again, this is speculation, very likely they use region of interest or ROI cropping. In other words, they say like, what's interesting to me? I'll look at that at higher resolution and discard other things. They could also use multi-scale pyramids, which is like you use high resolution data where you need it and low resolution globally. You could think of this as sort of equivalent to the human fovea in our eyes. And if you don't know the fovea, we only have a very, very small high resolution area that we look at, and we move our eyes around the scene to focus that high resolution area on our areas of interest. So of course, these cameras are not actually moving mechanically, but they can move the region of interest around and they can focus and they can use high resolution in those areas and discard the other information. And then of course, as Andrej Karpathy talked about several years ago, they can do temporal compression as well. They can use delta frames rather than full resolutions per frame. That's a trick that all video compression algorithms use. The video that you're watching on YouTube right now is using delta compression, which means that it only might be generating a couple of new actual frames per second, and the rest are just difference frames between the previous frame and the current frame. And this all allows Tesla to reduce the amount of information and do more sparse updates, and the effective pixel load per frame may be closer to 10 to 15 megapixels rather than 38 megapixels. So that's a really big deal. And then I want to discuss a table about latency breakdown, but I want to make a note that there's the physical activity of actuating actuators, right? You've got to move things through space. So for the car that's turning the steering wheel or pressing the brake or the accelerator, it takes a certain amount of time to do that. With Optimus, it would be moving the fingers, moving the body, etc. But you can do that in parallel with the rest of this process. In other words, you can make a decision, turn the steering wheel a half a degree to the right and press the accelerator a certain percentage or something. And while that action is being undertaken, while the physical activity is happening, you can already perceive the next frame of information and begin deciding on that. So you don't have to wait for the full actuation to occur before you can perceive and begin to plan for the next time step. So let's break this down a little bit in a table. We have sensor exposure and rolling shutter. That's internal to the camera. The expected latency is somewhere around 3 to 8 milliseconds, depending on lighting, etc. Then you have the raw readout going to memory. That's just feeding the data straight down the pipeline. That's probably around 1 millisecond because there's no ISP bottleneck. Then you have the vision encoder, which could be a CNN or a VIT. That's probably on the order of 8 to 15 milliseconds, which is the part that Ashok was talking about, the 1 millisecond per megapixel effective load here. Then you get spatiotemporal fusion, the occupancy flow network, all of that kind of stuff. That probably takes another 3 to 5 milliseconds, and that fuses all of the external cameras together and also fuses them in time with previous frames. So again, really, really fast. All of this stuff is happening incredibly, incredibly quickly. And next we get to the all-important planner, the brain, the actual thing that makes the decision about what do I do next. That could be as low as 2 to 4 milliseconds, which is really incredible. And that's consistent with version 13.2 latency being cut in half from version 12, because we had some information about version 12 and how much latency was involved there. So this is around half of that rate. And again, the fact that this brain can think that quickly is incredible. And then we have the control and vehicle actuation. And I'm just counting the beginning of this. This is not the full actuation. It could take a significant fraction of a second for these things to actually finish their actuation. But the beginning of that process, the command that would go to that, is another 3 to 5 milliseconds. And then the system can just pass on that and can perceive the next frame and start forward. So that puts us at somewhere around 22 to 38 milliseconds, which is on the order of the 30 to 36 hertz target that the camera frame rates allow. That is the maximum for these camera frame rates. And that is just incredible that Tesla is able to do this. And they're able to do this at very, very low power and very, very low cost per calculation. This triumvirate of things seems almost impossible, honestly. And it's just mind blowing that they're able to get this much performance out of hardware that is relatively inexpensive and runs within a very low energy and low heat dissipation envelope that can be handled on a mobile computer inside your car or inside of a humanoid robot. And just to make a note, human reaction time is on the order of 200 milliseconds and probably more for us older people, which means that Tesla is operating at around 10 times the speed of human reaction time, which is why the car can feel superhuman at some points. Now, it doesn't always, because I think that it's not making the absolute correct decision all the time, but when it does, you're like, whoa, it detected that, it made a decision before I even realized that. And I think with version 14.2, 14.3, version 15, AI5, etc., we'll get that feeling more and more and more often, where the car is going to feel kind of superhuman. It's going to feel like it's better than the best human driver because it just is. It's 10 times faster than a human in thinking about and reacting to all of these situations. So to finish up, let's talk about extending this into Optimus. Optimus is a little bit of a different beast. It's similar but different. So first of all, we've got the same AI4 encoder, and we will have the same AI5 encoder eventually. We've got the same transformer planners. We've got the same co-designed hardware and software latency model, but then we get to the differences. Cars have huge pixel loads with simple actuation. In other words, they're taking in a lot of data, 360 degrees, tons of megapixels of information, but the output space is very, very small. It's just a steering wheel angle, an accelerator press, or a brake press. That's it. Optimus, on the other hand, has far fewer cameras. They're probably at lower resolution, so you've got a much smaller input pixel load, but there is massive actuation complexity, not just because you've got 50 plus degrees of freedom in the bot, but because all of them interact with each other. With a car pressing the brake or something doesn't really affect the steering wheel that much. Now, it can if you're very severe about that, but in general, you can think of these things as kind of orthogonal axes, whereas with Optimus, all of the actuator adjustments, or many of them, have an effect on the other actuators. In other words, if the bot bends its knee, then it's leaning over and its center of gravity is changed and it has to adjust its body position, its upper body position. It has to move around in order to maintain balance. That's harmonizing multiple actuators at the same time, which a car doesn't have to do. And of course, you've got 50 plus degrees of freedom it's doing that with simultaneously. So you're trading off a massive input space with a very, very small output space for a smaller input space for a very, very massive output space. That's the really intriguing difference between a car robot and a humanoid robot. So we can speculate a little bit on what Optimus has in terms of its cameras. It looks like it has 2 head cameras. They might be running at 2 to 3 megapixels because, again, it doesn't need to see a half a mile away. It only needs to be able to see a short distance. It looks like it might have a couple of hand cameras or depth sensors, those probably running around 1 megapixels. So you're probably talking about 5 to 7 megapixels, raw megapixels per frame, and that's about 7 times smaller than for the car. And then, of course, on top of that, you can use the same temporal fusion trick as the car to reduce the effective load. But again, like I said, the actuator load is huge. You've got 50 or 60 degrees of freedom. You've got torque sensing. You've got touch sensors. You've got different loops running at different speeds. You've got a stabilization loop that's probably running around 1 to 2 kilohertz for balance, which is very, very fast. So those are running around 1 to 2 milliseconds with internal PID and MPC type of controls. Those have to run really, really fast so that the robot doesn't lose balance. But on top of that, you've got like system 2 type thinking where it's more rationalizing, it's path planning, it's doing that type of activity. And that can happen, almost down to like 1 hertz. It can happen like 1 decision per second if it needs to. Now, probably for smoothness of motion, you're probably talking about 10 to 20 times per second or something, but it can run much, much more slowly than the stabilization loops need to, because those need to keep the robot balanced and doing what it's doing without, shaking or overcompensating. So the likelihood here is that you've got a vision or scene reprojection internally of about 5 to 10 milliseconds. You've got the manipulation, and the whole body planner takes probably 5 to 15 milliseconds. And then the actuator commands, which you actually do have to pay attention to a little bit more with this, because again, balance and everything, are like 10 to 20 milliseconds. And that's limited by the mechanical response. So the overall loop is probably 20 to 40 milliseconds, with the really important balance stuff probably being run at like 10 times that speed, on the order of 1 or 2 milliseconds rather than 20 to 40. So there's a lot of different stacks of behavior that have to happen with a humanoid robot that don't have to happen with a car. So if you want to put that in a nutshell, you could say the car's bottleneck is pixels, where Optimus's bottleneck is physics. So what does this all mean going forward? Well, AI4 is likely near the physical limit of what you can do with CMOS sensors, plus silicon, plus the physical reality of actuators and thermal envelopes. AI5 will likely push into the under 20 millisecond territory with more temporal reuse, more tightly fused operations, especially on the front end, new camera global shutters, which will allow the entire camera system to shutter itself simultaneously rather than having to synchronize that after the fact, which has got to slow things down, and then integrated information like depth. And here's a bit of rampant speculation. It is possible that Tesla will adopt a hybrid strategy for AI5 cameras. So some high priority cameras like the front and long range ones will be upgraded to higher resolution, to that global shutter like I talked about, to larger dynamic range so it can see in the dark better, to even potentially self-heating for fog and ice resistance. And then the other cameras like the lateral cameras and the rear camera, etc., will remain with the current modules to save cost and complexity and reduce the amount of megapixels of input. But of course, they would likely receive firmware and processing improvements to upgrade them effectively. And the global shutter control that I mentioned is actually a really important part, because if Tesla can do global shutters and say every 20 or 30 milliseconds, we're going to fire the shutter off. So basically you're closing the camera, opening it, so that each one is deterministically opening and closing at the same time. That would resolve a lot of potential jitter in the signal coming in. It's possible Tesla's already doing this, but certainly by AI5 with the new hardware and everything, there is a high degree of likelihood that they will do that to again reduce the latency and increase the determinism of the input signal. And by the way, if it's not clear already, this is Tesla's moat. They have built end-to-end real-time inference at the edge. It's able to do this on a portable device, and it will only get better with improved software. And then of course, we'll take another big leap with AI5 when that comes out. And by the way, let me know if you want a full breakdown of what AI5 might look like and how much faster it could get. Alrighty, folks, that's what I've got for you today. It's quite a bit of information out of just a couple of sentences. I love to be able to do these breakdowns for you. Let me know in the comments if you appreciated it. And while you're down there, if you don't mind liking the video, it really, really helps things out. Thank you so much. And consider subscribing for more of this kind of content. And I will see you in the next video. Bye-bye.